Today I'm going to talk about shorter route synthesis of bioactive compounds by using the microdroplet chemistry. First of all, I would like to give a little bit introduction about microdroplet chemistry because students are going to learn. So when we see that drops water droplets, we call actually, like if you spray water, we call droplet. Suppose if the size of the water in micron, then we call as such, we call it as microdroplet. By using the water microdroplet, if you spray into the mass spec instrument, one can carry out the organic reactions. There are several methods were available. I will show few of them. Actually, by using the mass spec, normally we identify the mass of the compound, and by using the RB trap, suppose if we are taking the sample in front of the RB trap organic compound, if you spray into the mass spec in water, one can carry out the organic reactions. Something that was invented in around 2012 onwards, and this is the principle showed here. We are actually taking the sample in the syringe and then apply the voltage. When we apply the voltage, the particles are charged. Once they are charged, using the ESI electron spray ionization source, we spray that. The particles are sprayed here. Whatever the particles sprayed, they are charged. Here actually, due to the Coulombic interaction, reaction can occur. So once actually the positive and negative charge produced here, the ions will become smaller and smaller, and then reaction can occur. One can get the products in the mass spec. In this field, actually, there are two pioneers. Of course, Professor D. Pradeep actually also doing a lot of microdroplet chemistry. I will show some of the examples actually here. For the organic reaction, of course, actually, if you do the mass spec in a instrument way, we cannot collect larger quantity. It's very difficult. One can identify the structure of the compound by using mass spec. But for the organic reaction, this is the model we have devised, where we take the sample, mixing A and B in the syringe, apply the high voltage, and then just apply using the pressure, we spray the compound, and then we keep the collecting flask. Like depends on the size of the flask, one can increase the distance, but from 500 microliter, 500 ml to 2 liter flask, we vary the distance. In that way, actually, the reaction can occur. Only the reaction occur at the air-water interface in this area. So obviously, there are few parameter: voltage, flow rate, and pressure, and then the distance between collector and sprayer. That also very important for carry out the organic reactions. Here, actually, I have given one basic example. If you take a cup of water, and then if you use that, if you spray with a sprayer, one can convert into the useful disinfectant, which is nothing but hydrogen peroxide. How it forms? First, in water, actually split into H plus and then OH minus, and then further that OH minus loss of one electron, formation of hydroxyl radical. Once hydroxyl radical produced, it's highly active. The hydroxyl radicals are unstable. They go for further reactions, and then normally only water, it forms a hydroxyl radical formation of hydrogen peroxide. By using the microdroplet, this is one of the basic example has been done very long back. 2 plus 2 plus 2 cycloaddition reaction. So today I'm going to talk about most of the organic reaction, little bit related to the molecular materials. I will also tell what is that. So where actually this coupling cycloaddition reaction done by the Sharpless et al., who won the Nobel Prize 2 times, and they've done that reaction in 24 hours. Also in water, they are able to increase the rate of the reaction in 10 minutes. But if we sprayed it in water microdroplet, reaction is completed less than 1 millisecond actually, which clearly tells that reaction rate of the reaction has been enhanced several fold. So not only the organic reaction, also there are reports where actually Professor Zaire et al., they've invented also where actually normally gold nanoparticle has been synthesized in inorganic chemistry paper, one of the paper here I showed. But by using the microdroplet, just taking the gold salt and then if you spray, one can get gold nanoparticle. Here actually, after spraying, one can see the particle size has been reduced to 7 nanometer size. Also, one depends on the distance. By varying the distance, the size of the nanoparticle also can be varied actually. So also reaction rate has been increased compared to the bulk reaction. And another area actually I have shown here, Professor T. Pradeep and student Spurti, where actually they have taken the particles in a micrometer size by using the voltage, by applying the voltage in a microdroplet method, converted into the nanometer size. So here quartz crystals has been developed, and very recently this paper in 2024 in Science it appeared. Yeah, it's a lot of achievement has been done by Suburti actually. And until now, actually, there are several organic reactions were available. If you look in a microdroplet, one of the challenging tasks is still how one can get the chiral molecules by using the microdroplet method. That's one of the challenging tasks there. That's what my group aiming. I will discuss what is chirality, some few examples. Then later I will go on by the one examples. Here actually, if you know, I hope everyone knows about what is chirality. If we put two hands, if they are superimposable, which means they are chiral. They are impossible, it's achiral actually. Whatever that showed here, actually they are superimposable, it means they chiral. And also yesterday Hema discussed about proteins also in chiral in nature. And if we have a carbon, if contains 4 different atoms, which is also called as a chiral actually, because it's superimposable to the mirror image. This was actually, the chirality was invented in 1940s actually, sorry, 1840s by Louis Pasteur. Actually, I hope everyone knows about pasteurized milk. Pasteurized milk has been invented by Louis Pasteur in 1948, where actually he first actually tried for the wine actually, because those days actually the wines get spoiled quickly. Then actually, suppose if we do the pasteurization, one can keep the wine for longer time. That was invented by Louis Pasteur. So in his name only, the pasteurized milk, we are nowadays whatever we are saying pasteurized milk, whatever it invented by the Louis Pasteur. So same Louis Pasteur actually is said about, he has taken the wine from the wine tartaric acid, where actually you're able to see that L plus tartaric acid. He saw that sodium tartrate salt crystallized in the wine, then he determined the structure, then he found that actually it has a chiral molecule. That's what actually he invented. From there he invented the chirality of the molecules. After that, there are several chiral molecules were available in literature. Here I have shown here helicity of chiral compounds, or you can see the pasta, which also chiral actually. Whenever you see the pasta, actually it will be in only one side, you cannot see in another side. Actually, that's what actually they made. So even nature produces in trees, actually you see this is a helicity there actually. Here also similar in opposite. So it's a mirror image there actually. The nature also produces. I think some of them from China, another one is from Japan, I hope so. They are the trees where they are also chiral nature generates. Also perovskites in the materials field actually, where they make the perovskites by using the chiral molecules. They obtain the chiral perovskite, which is useful for OLED purpose or solar emitting diodes purposes. Even if you see that in the solar panels, so here actually this is the mirror actually, if we keep here, it's a mirror image, it's also chiral actually. That's what we are using in a phones or solar panels nowadays actually. So since actually there are several methods there for making materials also in chiral, can we use this microdroplet technique to make chiral molecule? That's a more important. It's also challenging. If you look actually in the chiral molecules where they involved, most of the pharmaceuticals are chiral. If they are actually chiral molecule, one isomer will be optically active, which will be useful. Another enantiomer is a problem actually, where actually which creates side effect. Sometimes it's an inactive form. So when you talk about a chiral, one chiral containing compound, one chiral center containing compound, which forms two enantiomers. I hope organic. So one is R isomer, another one is S isomer. Sometimes if the R is useful, S creates a problem. If sometimes S is useful and R creates problem, or maybe inactive, that's what actually in the medicinal industry it works, and that's why actually our enzyme binds actually with the pharmaceuticals. If both isomers are biologically active, suppose R also biologically active, S also biologically active, then it's a challenging. Then we must actually separate them, otherwise which creates huge problems actually. So one has to be separated by using various type of chiral methods, but by using microdroplet also can we do that actually, separate them R and S. That's what actually we are working on that. I will show some examples. Here I have shown thalidomide. Thalidomide, I hope everyone knows. Have you heard about thalidomide? Thalidomide. So in yes, you know that's so in 1950s, thalidomide used as a sleeping pill for pregnant women. But after few years, the newborn babies were affected with the thalidomide. So they were missing their legs, arms, or eyes. Almost 20,000 infants in European country born. Immediately that medicine has been banned, thalidomide has been banned, and still actually there are thalidomide survivors. And later actually a few years later, they searched in the thalidomide as a chiral center, which is S isomer creates the side effect. Because of that, lot of kids or infants actually miss their arms. Almost 2,000 infants immediately died after the birth actually. Even in 1950s, 20,000 baby actually for European country, it's a lot. That's why it's called as thalidomide war. After actually scientists actually thought that why not actually shall we use that only S thalidomide or thalidomide, which is highly useful in case of S is creating problem side effects. Then they've synthesized in the lab. Even that time only the chiral chemistry has been evolved a lot in the pharmaceutical industries. And later actually they administered to the only or thalidomide to the pregnant women, but still they found that there are infants were having the same problem. Then they realized what's going on. Immediately that medicine has been banned actually. Even if it is R is useful, we cannot use that actually. So then if you look that they found that the stomach acidity is too low. Like if you look at the pH of stomach acid, anyone has idea what is the pH of stomach acid? It goes to 1 in the range. So inside the stomach actually the R isomer automatically convert into the S isomer through epimerization process actually. What is epimerization? One chiral center converting into the another chiral center. Like R converting into the S or S converting into the R. It will be in the equilibrium. So that is called epimerization. What happened when they've taken the only one isomer, when they add actually acid inside the stomach, we have acid. That acid deprotonated the proton from here, and then it equilibrium here actually the chirality in between lost, and then again protonation occur, we get S thalidomide. So R has been converted into S, some point S will be converted into R. This is the biggest challenge that time, and we cannot then actually immediately that has been banned in 1962 onward. This has been banned. And how one can stop this problem actually? Can anyone guess how one can arrest the epimerization? Yes, by introducing bulkier group. Yeah, a double bond, obviously we are going to lose the chirality. Chirality is very important. Suppose if we make instead of actually hydrogen, if you have methyl group, there is no deprotonation, tetrasubstituted chiral center, hybrid amino acid derivative. So those type of systems actually epimerization can be stopped actually. That's what actually currently the detailed research is going on. So even today also one can see that thalidomide survivors. This was actually picture taken Ireland in 2021. There are 60th anniversary of, because it was banned in 1961, they have celebrated the 60th anniversary of thalidomide effect. Okay, this actually was big issue in 1960s, and thalidomide tablet want to promote to the US, and Frances Kelly, she said that she will not allow to US actually because the detailed study was not carried out. Then because of that, she won the Distinguished Pedals Civilization Award from the US government in later actually. Okay, so now actually I have discussed about thalidomide discovery, what happened. And nowadays actually there are tools. One can use the deep learning study or nowadays AI is also available. One can check first of all by using the machine learning, then which isomer will be useful by keeping the artificial enzymes. One can check actually, then also one can determine that. Here I have given another one important example, ibuprofen. I hope everyone knows that ibuprofen useful uh, for the painkillers. So, but if you look actually, yes, ibuprofen is useful, but our ibuprofen is no use. But many industries, many pharmaceutical industries, due to the separation of this pure isomer is very expensive. Then they mix, but fortunately, ibuprofen opposite isomer, it's not creating side effect, but unnecessarily we take some other chemical which is not at all useful for our body. Actually, this is one of the problem, actually, the inactive isomer actually. Also, I have given here naproxen. Yes, naproxen actually useful for the fever actually. Suppose if industries even add a little amount of or naproxen, which damages the what is that, liver actually. That's a one major problem. So whenever actually you are taking the naproxen, you have to check, are they pure? They are having little amount of another isomer which going to damage their liver actually. Normally separating one to another, it's very expensive. That's why some of the industries create these issues, but hopefully this will be stopped. Here I have given another one example, which is L-DOPA. L-DOPA, have you heard about L-DOPA, anyone? What is the use? Parkinson disease. Yeah, L-DOPA, for the invention of L-DOPA for medicine, they won the Nobel Prize in 2000. As well as in 2001, Sharpless and Novels, they won the Chemistry Nobel Prize. 2000 for medicine, 2001 actually for industrial application, they won the Nobel Prize. That shows that importance of L-DOPA. L-DOPA, if you look, S isomer is useful in the case of another isomer which creates another, it's not much biologically active, but we have to dump. So that's one of the problem. So there are challenges there to create pure chiral molecule. So as I've discussed actually in various medicinal industries, what about food industry? This also very important. Chiral molecules play a major role in the food industry, because in our day-to-day life we consume a lot actually the various food industries. Like here actually this aspartame, yes, aspartame, which is artificial sweetener, which is 200 times sweeter than the regular sugar. You may see naturally there are diet soda, spandula. I will show some more examples. But even 2024, before we popularly use the this spandula or diet soda, but nowadays there are study. But if we go for another, just actually changing the one chiral center from S isomer into the R isomer, which is bitter in taste. Just changing the one chiral center. Obviously, this molecule have 4 isomers. Out of 4, the diastereomer has actually bitter in taste. Just adding this another chiral center which creates bitter taste, then no use. So obviously chiral molecule play a major role in biological food industries. If you look, there are several several food products, they are using actually aspartame. Even day to day actually we are also using them. If you look the recent study WHO given in 2023, aspartame creates carcinogenic effect. So in future, whenever actually we use aspartame, you have to check, is it really required? So even a research article also in the Nature series actually it also produced actually aspartame creates the carcinogenic effect, which is available in 2024. Here I have given another one important example where actually how enzymes will bind with epinephrine. Epinephrine actually secreted in the adrenal gland. Suppose if we have another isomer of epinephrine, sometime actually our adrenal gland may not generate. Then actually we artificially we have to inject the epinephrine. Suppose if we are injecting another one, not going to bind, which going to cause the problem. So this also in the kidneys problem it will come. This also another one example. Even very recently we have used remdesivir. Remdesivir drug popularly used for during the COVID time. But if you look actually remdesivir molecule, there are 5 chiral center present in this molecule. So from if you have 5 chiral center, it creates several isomers. So making that also a lot of challenge there, but there are companies they make it. I hope now everyone knows actually importance of chiral molecule. What is the importance now? Is there any doubts? Okay, here I have given by using microdroplet how one can make the epimerization free or racemized optically pure form of amino acids. So amino acids normally when you want to make peptides or proteins, we have to make them protect the amino acid. If we are not protected, which makes unnecessarily other chains actually. So as electron, one of the important functional group for protecting the amino acid. Suppose when they protect the amino acid, after the once reaction is over, we have to deprotect them. So what happened in the existing methods, when they deprotect, they need to use enzymes. Normally enzymes are expensive in nature, or sometime actually we have to depend on the nature actually. So it's going to be lost actually. So that's a problem. There are reports there in the chiral chemistry where actually they make that from the acyl electron they are able to open up by using the binyl phosphoric acid. It's a chiral molecule. It's a chiral catalyst we call, and then it creates the new chiral center. But when they want to deprotect this amide bond, it actually epimerizes. So chiral become racemic. So it's a major challenge there in the acetylactone deprotection to deprotect to form the amino acid product derivatives. But suppose if you use microdroplet, here actually the problem happens because of that acid, it's a proteinate and then chirality has been lost. What we have seen in thalidomide, same problem happens here also. Even today actually, that's what, if you are using enzyme, then no problem actually, one can get optically pure compound. If you are not using enzymes, we are having challenge. Hence we have taken that task actually, and then if you use by using the microdroplet, we have taken the sample in a syringe, this acetylactone, and then mixed with the solvent, water and acetonitrile, and then sprayed into the flask, and then we have collected. Once we collected the sample, and then we have determined if that product is formed or not. Normally actually one can also determine by using the mass spec, but in this case we directly went for checking with the NMR instrument, where actually we have collected the sample. If you do the reaction, without reaction the product, the starting material is still there, and then if you do the bulk reaction in the same time in water, there is no reaction. Suppose if you apply the microdroplet method by spraying, we are able to observe that the deprotected compound with optically active isomer. And in different solvent we have tried, in water and acetonitrile produced a better conversion of product. Actually, this is the product formation. In case of bulk, there is no product formation. Later actually we also moved to the various other isomers. Here the major advantage is that because we are only using the water actually. Suppose if we use acid here, it will epimerize actually. So here actually the acid is not sufficient, water actually able to stop that actually epimerization issue actually, where actually we are moved various type of amino acid from glycine, alanine, all the cases actually, not the glycine, alanine, and then phenylalanine or tryptophan, most of the amino acid we have tried. All the cases we obtained that product in epimerization free actually, pure chiral molecule. Also the chirality has been determined by using the mass spec by using the HPLC instrument. This is the racemic compound where actually this standard actually has been synthesized as a peptide molecule to check the HPLC, and then where actually we made in the microdroplet method, we see that they are having the pure here. This is a major isomer, the little amount of minor there actually. It clearly tells that here actually epimerization does not occur actually. Here I am showed another one example where actually microdroplet suits the regioselectivity. When we do the bulk reaction by taking these 3 substrates like aldehyde, amine and indole, first actually this aldehyde amine forms iminium ion. When that iminium ion forms, which is highly active, then the nucleophilic amine, or actually this is C3, indole is C3 position nucleophilic enough, so nucleophile will attack. This is a C alkylation product. By tuning the microdroplet condition, we are able to observe, actually we observed that N alkylation product. Why actually N-alkylation products are important? But N-alkylation product, these all are called hemiaminal. They are highly unstable. Whenever we have actually 2 oxygen in a carbon or 2 nitrogen in a carbon, they go for reversible reaction to form the basic starting material again. Always these type of compounds are highly unstable actually. But if you look actually literature, this is one of the HCV drug analog clinically proven for HIV, where actually we have oxygen and then nitrogen core, which is actually there. And of course, you need to make industries, they do the longer steps to synthesize this type of molecule. Also here, there are antibiotics where actually nitrogen, both nitrogen in the same molecule. But in nature, actually, one can also get actually this type of molecule. Actually, they are also having the nitrogen near carbon, hemiaminal. By using the microdroplet method, we are able to achieve various type of compounds. Actually, I showed here by varying the electrophilic partner as well as nucleophilic partner aryl systems. Suppose when we go for aliphatic aldehyde, we are not able to get the product. Acetaldehyde we have taken, and then it forms first iminium ion. Then actually once iminium ion forms, this nitrogen going to attack here and then forms the product. But there is no product formation. Then we realize that actually this acetaldehyde boiling point is too low. Actually, it's at 20 degrees Celsius. When we spray very high pressure, it evaporates. Hence, actually, we are unable to get the product. Some challenges there in the microdroplet. Still, actually, these kind of things actually will be solved in future. Also, we have extended to the various other aliphatic aldehyde where high boiling aldehydes, we are able to get the product, butyl. All the cases we obtained the excellent yield actually. Now, actually, I showed actually where nitrogen bond compound containing compounds. Here, actually, I showed one of the example by using microdroplet method. We are able to make phenylacetic acid. Phenylacetic acid is very important core in various type of drug molecules. Here, one of them is penicillin G. Where if you look, actually, this is a phenylacetic acid core, or actually this ampicillin has the phenylacetic acid core. Also, several herbicides also having the phenylacetic acid core. So but if you look the literatures, there are challenges. They have longer route to synthesize. But by using the microdroplet, just taking the toluene and carbon dioxide, and then we sprayed, and then we are able to get that phenylacetic acid. It's one of the industrial application where actually most of the industries making the phenylacetic acid. Normally, how the industries make actually phenylacetic acid from the toluene, first actually they make the chlorination under photolytic condition, and then followed by sodium cyanide. So they do the SN2 reaction, then they get cyanide here, benzyl cyanide, followed by formation of salt, hydrolysis, and then they will get phenylacetic acid. But if you look in this method, industries actually you need to use the potassium cyanide or sodium cyanide. It's highly toxic. It's harmful. It's not something one can do that. But and also until now there is no report where actually we made actually until that actually there is no report where toluene converted directly into the phenylacetic acid. Actually, instead of touching the nose, actually there are methods actually one can go for longer route. But what we have done, we have taken the toluene, and then we have carbon dioxide which is electrophilic in nature. We made anion, that anion added, and then we get the phenylacetic acid. This was in 2023. If you look the mechanism, what goes in this, first water forms hydroxyl radical, so hydroxyl anion, and then loss of one electron, which forms the hydroxyl radical. This hydroxyl radical, as I pointed out, is highly active, which leave the one proton, deprotonation, it forms benzyl radical. Normally, benzyl radical also again it's unstable. It will loss of one electron, it forms benzyl carbocation, and then addition of one more electron forms the benzyl anion. This anion is highly nucleophilic, then added to the carbon dioxide, we are able to get the phenylacetic acid. So this actually we achieved, and then we have screened with various type of aryl derivative. Here I have shown another biologically important molecule where actually pharmaceutical industry is actually looking for that carbon nitrogen containing compounds. If you look in the pharmaceuticals, there are several pharmaceuticals contains this carbon nitrogen bond formation products, benzylamine core. All these molecules actually need to go for longer route synthesis. Instead of actually, if you use the microdroplet, one can make it in the, these are the one can make it in the direct step. These are the commercially available drug molecule where actually this benzylamine core present actually. Then if you look the literature, there are few methods: chlorination followed by amination, or oxidation, actually where oxygen actually add oxidize and then followed by nitrile formation under at 400 degrees Celsius, and then followed by hydrogenation condition. Or actually one can oxidize the toluene into the under strong oxidizing agent. By using that, one can convert into the benzaldehyde. Actually it will go for over oxidation, it forms the benzoic acid. Further actually under hydrogenative condition and amination, one can get the benzylamine. These are the methods were available. Normally benzylamines are synthesized. Popularly industries are by using these reports. But what are the drawbacks actually? Required to use UV light or higher temperature, higher pressure. If you look here, they used around 400 degrees Celsius and 5 to 550 bar pressure actually. If you want to go for industries in the very high pressure, it creates problem, as well as going for higher temperature reaction. But still actually industries are looking on this by using these methods. If we go for multiple steps or very high pressure and then temperature, we always have the challenges from the industries, pollution actually. So if you look the pollution report I shown here, India is the highest polluted actually. 2.33 million person died actually in every year actually in 2019 study it shows. Even today actually it increased now more. Also if you look the pollution study, now everyone knows actually Delhi actually more polluted. Why? Actually when we have multiple steps, industries actually generates byproducts. If we make byproducts free, this problem can be solved actually. Yeah, this can be easily addressed by using the mass spec instrument actually. By so what happen when the industries makes byproducts, sometimes they will throw, they should not actually throw into the sewage, but many time actually we see this problem actually it occurs. By using the mass spec also one can determine what are the contaminants there in the water actually. Of course Professor T Pradeep sir group actually working on those actually, what are the contaminants there in the water. Suppose if we make actually direct amination, then actually we are not going to create problems actually, which solve that major industries how they are doing that in various chlorination. When they use chlorination, they are having the HCl as the byproduct, or they has to, some excess of chlorine has to go out. So this all these things creates a problem actually. So what we have done, we have taken the sample toluene and water in dual spray. Actually earlier I showed actually mixture of solvent and water, but here actually toluene and water are immiscible nature. I hope everyone knows actually if you mix toluene and water, they are not going to miscible actually. Then very beginning we tried directly, obviously it forms two layer, it's not going to work. So for that case we have designed the setup where toluene taken in one channel, and then water and amine, which is nucleophile, taken in another channel, mixed here. Once mixed, and by applying the pressure, we are able to get the products, carbon nitrogen bond formation products. What we have seen in the food industries, sorry, in the benzylamine compound as a disinfectant, this is actually one of the disinfectant commercially available. We are able to make it actually. Also for that we have screened various type of solvent by using the mass spec. Normally whenever we do the microdroplet reaction, it's not immediately going to form the product. Always actually we have to screen that various solvent condition, how voltage will be transferred. So acetone, if you do the acetone, there is no reaction. If you do that in acetonitrile, here actually conductivity is less, and then methanol still actually. But if you do the reaction in water, only we have taken the toluene and then we sprayed, we are able to see that benzyl carbocation in water actually. But in case of other solvent, we are not able to stabilize the carbocation. If you are not stabilizing the carbocation, nucleophile is not going to add. So in the mass spec instrument, need to stabilize the radicals or carbocation. That's what actually we do that with mass spec instrument. So once we stabilize the benzyl carbocation, only spraying the toluene, immediately then whenever actually we started injecting the amine nucleophile, we are able to see that carbon nitrogen bond formation product. and then benzyl carbocation intensity has been decreased. Before injecting the nucleophile, we are able to see that clearly indicate that the benzyl carbocation is there. Once nucleophile injected, then product formation were observed, and we are also expanded to various other reactions. Actually, to reaction to check the monitor the reaction, is it really actually going on the radical mechanism or the cationic mechanism? For that, actually one can add the trapping agent. We used actually tempo is the one of the trapping agent, where actually tempo also has one radical, and then if the reaction goes via radical formation, tempo and that radical, actually whatever the intermediate forms complex, and then you will not get the product. So that's what actually happened, where actually we have taken the toluene, and with the tempo increasing the equivalent of tempo, we are able to trap the radical intermediates. Benzyl radical has been benzyl radical has been tapped with the tempo. Tempo, I hope, which is tempo, it contains the 6-member ring containing nitrogen oxygen compound. Actually, you can look what is tempo. So this tempo actually trapped the benzyl radical, then there is no reaction. Then we are able to see that this clearly tells that reaction goes via radical mechanism. Further, actually, once we identified, we proved the mechanism, how it goes. Actually, first formation of hydroxyl radical, this radical deprotonate and then forms the benzyl carbon radical, and then further one loss of one electron, which forms benzyl carbocation. Now benzyl carbocation is highly stable actually due to the resonance, so it forms the triplyman ion. Actually ring opens and then forms the 7-member ring. That's why actually this also aromatic, this also aromatic, so one can stabilize the benzyl carbocation. Then whenever we add a nucleophile, which clearly forms the product, you see actually whatever we made actually, which is also similar type of scaffold, which is also available in the market as a disinfectant. So if you look the reaction time, always all the reactions completed in less than millisecond actually. If you do the industrial scale industries, we have to rely on longer days or many steps actually, but microdroplet reduces the time as well as number of steps. Here I have showed another one important example where phenol synthesis. Earlier I showed carbon nitrogen bond formation. Why not carbon oxygen bond formation, sp2 system? Earlier sp3 system I showed. So where actually, if you look actually, phenol was used for doing the surgery in 1865. Those days actually Louis Pasteur from UK, actually they use that phenol for spraying that, whatever we do that today spray, same thing they have done that during the surgery. They spray the phenol disinfectant, they have done the surgery actually. Same thing can we make in a lab scale by using the microdroplet method. Suppose if we are taking the starting metal instead of phenol go for oxidation reaction. I hope phenol oxidize. Any idea what happens? Oxide, further it goes for quinone formation, several things happens. Further it goes for oxidation. But suppose if we take stable benzoic acid, one can use longer days actually, which is more stable. If you see day-to-day life, there are several phenolic group containing compounds are bioactive compound. And suppose if we are taking the stable benzoic acid, which is cheaper in nature, and then mix with water, benzoic acid, water, actually they are miscible, and then one can directly spray. So one can get the phenol, which is disinfectant. Even for day to day, we are cleaning purpose, we use phenyl. Actually, it comes actually from here, phenol actually. If you look actually how industries make, this is one of the recent study, 2021, by using the lithium hydroxide and then copper mediated and oxidation condition using the photolite, they are able to convert a decarboxylation phenol, recently published. And also there are another one report were available from benzoic acid over by oxidizing by using the MCPB, metachloropyrbenzoic acid. Since actually I could have drawn the structure, I hope metachloropyrbenzoic acid, benzoic acid, everyone knows you are having one more oxygen actually, which is oxidizing agent actually, where metachloropyrbenzoic acid they used oxidize and then further electrolyzed, get the phenol. These are reports were available. But if you look, both method requires multiple steps or it requires actual metal reagents. But what we have done, we have taken the benzoic acid in a syringe, mixed with water, no metal, no multiple steps, single step, we are able to obtain the phenol in the larger quantity actually. So for that actually we have screened various temperature, various flow rates, solvent, voltage, all the things. And then here actually one of the studies showed here by varying the distance, collecting distance, by increasing the distance from sprayer and collecting chamber, we are able to convert phenol more actually. The intensity has been increased. Also by varying the voltage, we found 4 kilovolt actually. When we apply minus 4 kilovolt, we are able to get that more compound formation actually. So not only the phenol, we also done the using 4-bromobenzoic acid, decarboxylation occurred, and then the phenolic compound has been formed. So if you look here actually, we have actually M and M plus 2 equal intensity, which tells that what? Any idea in mass spectrum? Hope some of them are. Yes, bromine present actually. So if we have the peak M and M plus 2, because it's an isotopic ratio, isotopic abundance of bromine 79 and then bromine 81, they're almost 1:1 ratio. So that's what actually, which makes actually M and M plus 2 peak, which clearly tells that product formation. And also where actually nitrosubstituted compound, electron withdrawing, or heteroaryl systems, Friedel derivative, decarboxylation occurred, one can get that hydroxyl compound. Also, if you have multiple acids, we have multiple triacid, mono decarboxylation, decarboxylation, and then tri-decarboxylation. All the products we are able to observe in the mass spec instrument. And further, actually, that has been determined by using the MSMS study. Actually, further cleavage, one can see the mass spectrum, which clearly tells that formation of this product actually. To identify that reaction is going via microdroplet because of the water or some other, because we need the water OH from decarboxylation of this benzoic acid if you want to convert it into the OH. So then instead of water actually we have taken the H2O18 labeled water, where actually we are able to see that O18 labeled product, which clearly tells that the OH comes only from the water actually under microdroplet conditions. Further, actually, we also screened with the tempo, where the reaction goes via radical mechanism, and then we have proved the mechanism. So I showed actually aryl oxygen bond. Similarly, aryl nitrogen also we have formed actually, where actually benzoic acid has been taken and then mixed with amine, benzoic acid, water, all are miscible in nature, no problem here. So we've taken in the syringe, simple setup, apply the voltage, sprayed into the instrument, we are able to see the carbon nitrogen bond formation. We have screened various type of, we have obtained various type of carbon nitrogen bond formation product, alanyl compounds, and then mechanism showed here by using the mass spec. That's one of the important tool. Other than mass spec, no one can prove all these mechanism. Earlier we always write actually in organic chemistry, we write the mechanism, proving the mechanism have challenge, but by using the microdroplet method or by using arbiters, so not for the microdroplet, one can stabilize in water actually, one can stabilize various, all the intermediates, one can stabilize it because of the water actually. So what happened first actually, this when we are taking the water forms hydroxyl radical, hydrogen peroxide, and then ammonia adds, forms hydroxylamine. When this hydroxylamine is highly nucleophilic nature, adds to the benzoic acid, forms this acetal type of compound, because this is electrophilic in nature. Now it adds to here, and then we get acetal, and then proton transfer followed by formation of this type of amide, which goes for under Larsen rearrangement. During 12th class, I hope studied Larsen rearrangement. So further Larsen rearrangement, and then leaving the carbon dioxide, one can get the aniline. So that's what. So all the intermediate has been cleanly proved by using the mass spec analysis. And where actually I showed carbon nitrogen bond formation with aryl system. One of the challenge in organic chemistry, vinyl systems, where actually sp2 systems, if you have acid, if you want to convert these type of systems, are highly difficult in organic chemistry. So this is also one of the challenge we have taken. And then where we applied similar method, we also able to get the vinyl carbocation, and the nucleophile has been added. We are able to see the carbon nitrogen bond formation. Now here actually not only the carbon nitrogen, carbon sulfur bond formation also we are able to get. Further we have extended to the carbon phosphorus bond. If you look in the literature, where carbon phosphorus bond by using the Grignard condition, they were done at very low temperature, minus 78 degrees Celsius. Doing the Grignard vinyl systems are challenging actually. But by using the micro droplet, just water and applying the slightly voltage, taking these two starting metal, even here actually activator, here this phosphine is not activated actually. We are able to get the carbon phosphorus bond formation product. Those products we are able to identify by using the mass spec as well as tandem mass clearly tells the product formation. So until now actually I showed about how carbon-carbon bond, carbon-oxygen bond or carbon-nitrogen bond formation. In a chemistry, we are also having that how one can break the bonds. It's also one of the challenging tasks, not only the forming the bond. Sometimes we need to break the bonds. Here I showed lightning. So now today also you may see that lightning effect during the rain time. So what happens lightning actually creates where in the cloud formation of positive charge and negative charge, it creates lightning. This lightning one can use, one can carry out the reaction. For that effect we have taken, where actually we have taken the micro lightning study, where we have taken the alkynes in the chamber, generated the lightning effect here by applying the voltage and very high pressure, spraying the water, actually only spraying the water, manually created the lightning effect. And then here the alkyne vapors, alkynes are low boiling compounds, they evaporates automatically if you open the flask. You open the alkyne and then here lightning happen. That lightning that has been identified by using the laser actually. So the lightning breaks the bond. So I hope everybody studied during 11th class alkyne ozonolysis or alkene ozonolysis. If you do the ozonolysis of alkene, what is the product will be expected? Acid. Yes, acid or aldehyde. Of course actually it will go for over oxidation, one can get the acid. So same thing actually, but ozonolysis is a challenging task and ozone carrying out in a simple lab, it's not possible. In India, very rarely few labs only do the ozonolysis reaction. It's not easier, though actually there are mechanism there, but still challenging task in the lab to work. Also record to do the reaction at minus 78 degrees Celsius under ozone condition. But by using the microdroplet method, we have taken the alkyne in the chamber and then we just open the alkyne. The boiling point of alkyne is too low. It evaporates and then manually created the micro lightning here. The lightning will break the carbon-carbon triple bond. It breaks the carbon-triple bond. We are able to get the benzoic acid. We observe this. So further actually, we have screened various solvent, various like what happens actually with oxygen or without oxygen. So whenever actually we pass the oxygen, we are able to see that product benzoic acid formation. Whenever actually this sprayer is connected with the nitrogen gas, there is no product, starting material, only alkyne. Once actually oxygen enters in the system, sprayer shows immediately formation of benzoic acid. That's what clearly observed actually. We are actually on and off, passing sometime nitrogen, sometime oxygen. So we see that oxygen goes into the ozone and then formation of oxygen radical, which forms the generate the ozone actually under lightning effect. So once ozone is generated, which is highly unstable, and it go for the cleavage of that product. We also various actually from the aromatic system into the aliphatic system, where we are able to cleave the triple bond. Here also this cleaved product M and M plus 2 clearly tells that a formation of the ozonized product just using the oxygen and water and of course starting material alkyne. So now actually we don't need to use any ozone. Ozone is also dangerous to handle in the labs and not dangerous, it's difficult to synthesize as well as need to carry out the reaction at very low temperature. So another one of the challenge there in organic chemistry, this paper actually appeared in 2023, where actually in chemical and engineering news showed that actually coupling reactions are not possible without metal. There are papers appeared before 2023, but after they showed that not possible actually without metal, Hereafter, no one can say it's not. But that's the way actually, if you read the paper, you'll have idea. Metal free is one of the major mistake. We have taken actually this is one of the challenge there in a chemistry. So shall we solve this problem? For that, actually, we have used the microdroplet technique. It's appeared in Nature Catalysis. All the paper, there are papers, all of them withdrawn. All of them, whatever before, even it's a Nature Catalysis 2021 paper also withdrawn because they published with metal catalyst free actually. Then why not actually microdroplet? Can we do that? Can we solve this challenging problem? And then we have taken the alkyne and then phenylboronic acid and then mixed with water, we are able to get carbon-carbon bond formation. Of course, it's along with Sandeep Bose, one of your group member actually is currently at postdoc is doing. Obviously, I told we have done together actually at Stanford actually this work. Where actually, if you look actually in organic chemistry, this Sonazera type coupling reactions, even in the same Nature Catalysis paper, they have done that same paper, but it has been withdrawn. We are sure actually it happens, but in microdroplet condition, one can do that metal-free reaction. So where we have taken the sample and then alkyne and phenylboronic acid into the syringe pump and then apply the voltage, and then by using the nitrogen gas, we are able to get various type of carbon bond formation, triple bond formation products actually. So coupling reaction one can do. Now we have done that Sonazera type coupling. Hopefully soon somebody will publish with Suzuki coupling. There are several types of coupling reaction, noble coupling reactions, but now hopefully some other coupling reactions may appear. And once we form the product, how the reaction occur. If you look these coupling products, they are all a potential drug molecule, commercially available, they are drug, but still actually need to go for metal based chemistry. What happens actually when they do that, most of the coupling reaction done by the palladium coupling, any idea actually what happens if we do the reactions using metals? Metal actually, whenever we do the organic chemistry, we purify the compound by using column chromatography, by using the silica gel. What happens? The silica gel metals actually slightly leach out, and then always actually the organic compound contain trace amount of metal. Many times in organic chemistry, we try to use NMR instrument. NMR instrument not going to show that any metal present. Then we'll have challenge. Industries have the challenge. If you have trace amount 0.1% of metal present, it's very difficult to identify. Industries make the tablet actually. If these are, for example, these as I showed you, all are potential drug molecules. And then if they make, they have the challenges to remove. That's why they will do multiple purification. Still have challenge actually. But suppose if you use metal-free method, it will be solve that problem. So if you take with metal, which creates side effects, that's one of the major problems. Some of the metals are poisonous in nature actually. So that's why many time actually coupling reaction which don't allow you to use the poisonous metals. If you look in the microdroplet method, first the hydroxyl radical cleave the bond here, carbon boron bond, and then formation of radical, and then loss of one electron, formation of phenyl carbocation. Normally phenyl carbocation is highly unstable actually, but under microdroplet condition, the water stabilize that. Air water interface stabilize the carbocation, and then the nucleophile from the phenylacetylene, it adds, one can get carbon bond. So this has been showed, we have showed to the reviewer actually, that's what going. And then we also showed what on the paper which retracted by using the metal free method. They also agreed, yes, this happens only in microdroplet. That's what actually it appeared recently in 2025. Yeah. Oops. All the intermediate has been identified by using the mass spec method. And this is one of the last study I will show, where actually by using the microdroplet, one can make the drug molecules. Anyone knows actually which one is the expensive liquid in the world? Other than faculty members, please. Everyone knows. Any idea which one is the expensive liquid in the world? Is the water is expensive liquid? No. Guess, students. Which one is the expensive liquid in the world? So there is no venom, blood, all are expensive, correct? If you look actually, this is the Google image where I showed here. Scorpion venom is the most expensive liquid in the world. It's a per gallon, which is approximately 3.8 liter, cost is around $39 million. 3.8 liter. So scorpion venom, actually you can imagine approximately 325. Now actually the dollar rate change, it will be more now. So it's even 3.78 liter of scorpion venom is 325 crores. So 1 ml is almost 1 crore. It comes in that range. Sorry, no. 10, yeah, 100 milligram. Okay, so actually if you look, actually 1 liter approximately 100 crore it comes approx actually. So it's very expensive. There is a team, they visited Stanford actually. That time I was postdoc. Then obviously we are still collaborating with them. So they visited Stanford and then they were given scorpion venom from the Mexico. Scorpion venom is a potential drug molecule. They are using for natural therapy in Mexico. And then they showed that because of these Mexico scorpions are killed, and they've given the sample, and then we have tested by using the mass spec as well as by using the NMR study. We are able to identify these structures. Obviously the scorpion venom has several other compounds. These we are able to identify there are 3 molecules. Among them this is a blue venom. Actually it's a blue color, and then this is a red venom. The blue venom, which is useful for tuberculosis, it's against bacterial infection actually. So one of the challenging one actually, where actually we have synthesized after that. Suppose if we make it in the lab, we don't need to depend on scorpion. So scorpion venom is very expensive. They were using for TB. But suppose if we make it in the lab, we don't need to make a skill, or we don't need to take it from the scorpion. It's very difficult actually. Whenever you want to take 1 drop of scorpion venom, sometimes they apply the shock treatment and then to get the venom, but sometimes they kill also scorpion. It's a very challenging task. But if we make it in the lab, the cost going to be reduced. Otherwise, we have to go for 325 crore for 3.78 liter actually. So what we have done, we have synthesized in the lab in a multiple step. Whenever actually we go for one step to another step, we lose always yield. Even if we start with 10 gram, at the end, maybe after multiple step, we may end up getting few milligrams or few grams of compound. It's very difficult. So here actually at the last step also, it's one of the step where retro-disorder reaction occur. Where actually this is the carbon-carbon bond breakage happen. Disorder reaction, I hope everyone knows. 4 + 2 cycloaddition reaction. And the retro-disorder reaction is a reversible reaction. Where do you need to apply very high temperature actually? Normally in this reaction we applied 120 degrees Celsius. Can we make this molecule by using microdroplet method? So here actually the reaction done for 12 hours actually. Suppose if you reduce the time, then what happened? Like once the product formed, if you do keep on heating the flask, it's going to decompose. That's a challenge. The compound going to be decomposed. It's a quinone compound. Suppose using microdroplet, one can make it in a shorter time actually. There are several other quinone containing molecules or potential drug molecule were available. By using microdroplet, in which time is less, I will just conclude. By using microdroplet method, we are able to convert the disorder product into retro-disorder product in milliseconds. And for that actually we have designed the setup for high temperature reactions, where actually we spray the sample and then we keep the coil here, the coil which heats up. Because retro-disorder reaction without heat, it's a chemistry cannot occur sometime. So we have tried without heat, but it does not work. Then actually we apply the heat here only in milliseconds. So whenever the sample spray here, it will pass here and then it will be collected in the room temperature flask. So only few millisecond sample has been heated here. But in case of bulk reaction, you have to heat continuously for 12 hours, which produce multiple byproducts. But here it will not. Either starting material or product. If some starting material there, one can go for another cycle. That's the advantage with the microdroplet method. So we obtain the product in few milliseconds, and compared to the bulk reaction, this method is 10 to the power 6 times faster than the routine bulk reaction. Even though we have done that, still actually we have done further next into the microdroplet method. Earlier bulk reaction also done by our group actually. So this is the one of the challenge. Silver alginate is useful for wound healing. Everyone knows, correct? Whenever you have a wound, if you go to the hospital, they put the silver band-aid or silver alginate band-aid. It's very expensive. Suppose if you make it in the lab, what happened? Why it's very expensive? Any idea why actually silver band-aids are shipping, and then where the industry made, and then sometime it go for decomposition, all those problems there. But suppose if you make it in the lab, in the hospital, in situ, it reduces the cost of the silver band-aid, where actually we have taken the silver nitrate in water or here glycerol, and then we have sprayed and then collected. Of course, Professor T. Pradeep also done. We have also worked on that similar type of area actually, where actually we are able to get smaller particle size of silver nanoparticle. We also devised the setup commercially. This currently actually commercialization process is going on, where we have taken the silver nitrate in water, we sprayed, and then we directly one can spray into the wound, and then we don't need to use any band-aid. Silver nitrate is very cheap. Just mixing with water, one can spray silver nitrate silver nanoparticle can be formed. That's what actually we made. Also by using that, we also varied that. So we also synthesized these type of oxidized products by using the silver nanoparticles. And whatever I have discussed, all the organic reactions, currently actually by using microdroplet, some mass spec instrument, imaging study also one can, this is actually for students, what's going on currently, that's what I thought to tell, where actually by using mass spec, one can also identify cancer cell or non-cancerous actually, can be determined by using that, how they are denatured, their mass spectrum pattern will be different. Also by using the SWOT analysis, also currently work is going on at Stanford, where actually take the SWOT of the human, one can tell that a person is healthier or affected by the disease actually, by just using the mass spec instrument, fingerprint. So these all are immigration purpose, it will be useful. Currently this is the high level research going on. Hopefully this mass spec tool will solve a lot of few issues in the world, and there are few reports were available to make drug molecules, but still some more other methods will come in future. Yeah, thank you then. Yeah.
Questions? Sir, in the coupling reaction where the boronic acid and the alkyne is taken,
Yeah.
and the coupling has happened, but there is a case where alkane can undergo ozonolysis also.
Yes.
So
Yeah, that's a
both are
byproduct there in that reaction. Yes, it will be the byproduct. Yeah.
No, both are happening like.
Yes, actually, whenever the nucleophile and electrophile there, of course, it goes for the reaction. There is no electrophile. Then obviously, actually, there actually in that case, actually, boronic phenyl carbocation act as electrophilic nature. We have phenyl carbocation, anion is ready, and then they interact. There is no anion, there is no cation, then we have trouble. Then actually, it breaks the bond, because one already actually available in the system, anion. Let me show the mechanism. Yeah. In the syringe pump, whenever we spray, both anion present as well as carbocation present. Once actually sprayed in the due to the coulombic interaction, immediately they are going to attract. So this nucleophile going to add to the electrophile and then formation of product. Suppose there is no electrophile, then obviously yes, we also observed that also we have given. We also observed where actually benzoic acid product formation actually, where actually this cleavage of this bond, yes, it will be there. That's a byproduct. Because this is one of the challenging tasks, hence we have taken. Normally ozonolysis of alkynes are popular. Sorry, alkenes are popular, alkynes are challenging actually. That's why by using mass spec, it's a possible. That's what we showed. Even in 2000, there is a study, only the theoretical study, one can do the ozonolysis of alkynes, but commercially actually it's not available. That's what we have done there. Yeah.
So very nice work. Just a few things. You said you have converted silver nitrate to silver nanoparticles. Is it in the nebulization?
Yes, nebulization. Yeah.
How can you ensure that 100% conversion? Like, did you check the conversion rate?
Yeah, those are the study actually currently going on. Of course, how? Yeah.
because when you say it can be directly applied to the skin,
Yes.
silver nitrate is harmful for the skin.
Yeah, that's true actually. That's what actually we have to do, the varying this distance. Suppose if you are varying the distance from sprayer and collecting sample, one can convert actually. That's what actually, this is the optimization has to be done.
Okay, no,
Yeah.
actually I have worked on this.
Yes,
for
you are right.
many
Yeah,
years.
right.
I know that may not be 100% conversion.
Yes,
There are
actually-
a lot of precursors that stay alone.
Yeah, we have to optimize the condition to get 100% conversion, because this is a preliminary study. Yeah, more work will go on actually. Yes.
And for that, if you were like chiral work, I think it was slide number 30, when you said there is no protonation, that's why the epimerization doesn't happen. But you are using high voltage, right? And water.
Yeah.
So for the electrospray, so protonation is pretty much feasible. Like
Yes,
known.
that proton is H plus is not sufficient to epimerize the chiral center. That's what actually, because what happened once we observe the product here, actually it's not only from the mass spec. Of course, we have taken the sample, and then we have, these all are actually identified by using the HPLC, and then we are able to see that they are not epimerized, they are single. Suppose if they are epimerized, what happens in the HPLC diagram, we'll have both. This is the reaction mixture from the microdroplet. This is that actually non-microdroplet method. So in case of non-microdroplet, this is R isomer, this S isomer 50-50% there. But in case of microdroplet, the one isomer is major. Of course, 5% of minor there actually. That's what we have written, 90% enantiomeric excess. 90% of one isomer is excess than another actually. Yeah.
Thank you.
Because it's only the water. Yeah, it's an of course actually here also obviously actually one can vary that voltage, all those things study can be done. Yes.
So it's about the same Suzuki reaction that you have, Suzuki kind of reaction that you're doing.
Yeah.
So you showed that there is a formation of phenyl, this cation on the benzene.
Yeah.
Phenyl.
Phenyl carbocation.
And you said that this air-water interface is stabilized.
Stabilized.
The cation.
Yeah.
But so like it's like surprising that the formation of phenyl cation is itself a surprising. So I want to know what kind of interaction.
Yes, there are study actually like what happened. We have carbocation, we have phenyl carbocation, and then hydroxyl anion will be there. They are actually surrounded actually by the water actually. So the carbocation is caged with water. So they are stabilized in the mass spec instrument. Of course, it's not in the isolated environment, in the inert atmosphere. It has been stabilized longer time. There is a study. Even we also keep that if we are not stabilized, the phenyl carbocation is not stabilized, we cannot observe in the mass spec. So the phenyl carbocation has been observed longer time. That's what actually whenever we do the reaction, first we check that whether the carbocation or carbanion are we able to stabilize. If we are able to stabilize, then only we can do the reaction. Suppose if we are not able to stabilize, just mixing together, no reaction actually. Yes, that's an important study. That's why actually where I showed benzyl carbocation first stabilized in some other cases, and then after that we have added nucleophile nitrogen, then forms the product. Yes.
It's a very nice talk and then very nice
Yeah, thank you.
research topic you given to the community. But I just want to learn that you said like there is a role of this collector, right? I didn't really understand that where exactly this chemical conversion is happening.
Okay.
And then what is the role of this collector? And you say like that distance matters
Yeah,
a lot,
yeah,
right?
yeah.
So if you just put a
Yes.
light on that.
Yeah. Yeah, for example, in this reaction. So until this actually where we apply the voltage here, and then the particles are charged, and then due to the pressure, they are going to spray. Until that, there is no reaction. Until this end of the tip of the tube.
Okay.
That also we study that reaction without applying the pressure.
Here, where is the collector? In this particular.
Also, this is the collecting against the round bottom flask.
Collect the droplets.
In the flask.
Okay. So then the collector doesn't have any role, right?
Yeah, yes, actually, like for example, suppose if you are using 50 ml flask, the distance between sprayer and then collector means actually the bottom of the flask, surface of the flask, it's only like maybe 10 centimeter.
So you mean like the kind of
distance.
The travel time of the
Yes.
droplet?
Yes.
Because how much time it
Travels.
floating in the air? Is that something like
At the interface.
droplets evaporating? Okay.
Yeah. So actually what happened, by increasing the distance, one can convert that more actually. But some cases actually what happen, it decompose if we increase longer further. That's why actually what happen, for collecting purpose we start from 50 ml flask, 100 ml. It means that actually it's not 50 ml flask, actually the distance between collector and then surface of the flask actually going to be increased.
It's also a matter that whether it's directly fall on the solid surface or it just fall on the liquid, that product.
Yes,
It has something-
yes, it will have effect actually. Slight differences will be there, but mostly actually once we are collected here, so no more reaction. That's what actually we expect. And then many cases actually we also cool down the
So
flask actually.
I ask these things because it's definitely there are a charge around the droplets, and
Yeah.
then also if you strategically choose some surface which can probably give some sort of tribal electricity, may be prolonged or something. So that's the
Yes.
probably another thing.
Yeah, this
to look
also,
after.
as you point out, sometime reviewers ask this actually, like where actually we keep, actually we cool down the flask, so suppress the reaction, we keep it at very low temperature, and then we check that is it really occurs at the thin layer, actually thin film, or at the surface of the at the air water interface. For that also control study we do that, and then we always actually
No,
show
I'm
that.
saying all of this because if you want to go for a large scale,
Yes.
and it really matter this interface, probably some sort of surface function strategy could be very useful in
Yeah,
terms of
yeah.
promoting promoting this tribal electricity, and then
Yes,
how
for the
charging
larger
it.
scale, yes,
Yeah.
of course, actually it's possible. You are right, actually, that this study has to be done. Whatever we are always we do in miniature size, but of course larger
Sure.
size has to be done. Yes.
Extremely good talk. So
Thank you.
microdroplets are known to break CF bonds also.
Yeah.
So that is the one of the strongest bond possible.
CC bond.
CF bond.
C bond. Yeah,
bonds.
yeah.
Recently Siddharth.
Yes, Siddharth.
So that means my question is little bit in a broad concept. So how these molecules which you are synthesizing, they are stable, because if that microdroplet can break CF bond,
Yeah.
it can break anything.
Yes.
So how the molecules are stable?
Yeah.
That is a very wonderful thing to talk.
Yes, you are right. Actually, whenever we do the microdroplet reaction, it's not only the product formation. Of course, side products will be there. Multiple products will be there. These all can be suppressed by varying the conditions, by varying the pressure, by varying the temperature, or by varying the distance between sprayer and collector. Suppose if it is very high pressure, sometimes we may not see the product. So that's what actually the pressure play a major role. We vary the pressure from 50 psi to 120 psi. Sometimes reaction required 50 psi. Where recently one of the chiral chemistry we are working, where we need only 50 psi. If we go further, it's the racemization occurs. Actually, that's one of the chemistry we are doing. Yeah,
Thank you.
it's possible. Yes.
Very nice talk.
Yeah,
I
thanks.
have. Can you go to the next slide? I wanted to ask you.
Yeah.
While we do all of these experiments,
Yeah.
are there things that we don't know enough? Are there more things? For example, you seem to be saying that the interface is controlling the transition state.
Yeah.
Right.
Yes.
Kind of.
Air water.
The interface is somehow controlling one enantioma.
Yeah.
Which is implying that solvent is inducing some form of a chiral control. So if you were to then extend it to water, this is not water, you might say that interfacial water is chiral.
Yeah.
You might say that some other solvents are also chiral. So if you look at all that space, there is something truly interfacial chirality. If we can look at that in greater detail,
Yes.
something more is there for us to
Do the
learn.
Yeah.
What is your thought on that?
Yeah, right now, actually, frankly speaking, when we do the reactions, many cases actually it epimerizes or racemizes actually, but there is a still actually hope there actually one can get actually, where actually we have taken here it's a chiral compound, and then we are not epimerizing it, we are not racemizing. But as you asked, actually, if we start actually starting metal is a racemic, and then can we get chiral? That's a challenging task. It actually how actually the water approach in one side actually. For that actually maybe the water or hydrophobic hydrophilic site has to have some kind of steric hindrance need to be made actually. That's a
Very good. So a lot of
that's a
talk,
possible
lot of
thing.
study is studies are essential.
Yes.
Now, you know that there are 54 students from different parts of the country. Your talk has opened up the possibilities, enormous possibilities. With simple equipment, one can go
Yeah.
and do many things. There are probably 40 different research groups that are present here. What kind of comment, what kind of suggestions can you offer for them to explore
Yeah.
and open challenges in this area?
Okay. Actually, so in case of microdroplet chemistry, one major advantage that we are using that water are mild condition, just applying the pressure. But there are challenges going for the larger scale. If we make actually here, if you look actually the setup, it's very simple. Actually, just taking the tube, and then passing the sample, and then we collect. But the challenges here is that actually how actually control the reaction, only the product. As there are few questions came, byproducts formation will be there, and then as well as going for the larger scale. Can we go for kilogram scale or gram scale? Still actually challenges there. There are few reactions were available, one can do, but otherwise in a routine organic reaction, any type of reaction, one can try actually. If you try, if you succeed, that will be really interesting actually, because in organic reaction, there are several organic reactions known in a routine organic method actually. But by microdroplet, it's a new area, emerging area, one can get the product in a milliseconds. Normally, the advantage, as I pointed out, if you go for a heating flask, many time actually the photolytic conditions, reactions, one cannot go for larger scale. That's why industries have challenges doing the photolytic reactions. But microdroplet reaction, where reaction occur at the surface, so one can do that. Or similarly, flow reaction. Flow reaction also has a challenge, but here once you sprayed, there is nothing going to happen. Your collected compound actually. So that lot of challenge there. Sorry, lot of advantage there. Hopefully, student can explore actually. Yes.
One last bit that I would like to suggest is that maybe this area, colleges can do a lot of work in this area. Outreach is important.
Yes,
here.
that's
And what can you do in that area? I do a lot of outreach in different places.
yes.
With simple experiment,
Yes, setup.
I remember it's hydrogen peroxide.
Hydrogen peroxide
Yeah,
issue.
that.
Yes.
So what can one do to take this kind of science to colleges with limited infrastructure?
Yes.
All you need is some
Yeah.
paper strip kind of
Yes. Yes.
tools.
As you point out, it's really well taken. Yes. For example, benzaldehyde is liquid in nature. Suppose if we spray using microdroplet method, we get solid actually benzoic acid formation, immediately formation. So one can make actually benzoic acid larger scale. This type of study, like basic reaction, but without any reagent or catalyst, one can do. Yeah, you are right. Yes, I will do that outreach study. Thank you, sir. Actually.
Wonderful. I'd like to offer another way to think about this that might be useful. The reaction is really happening at the interface, hydrophobic, hydrophilic interface. You need water. It won't happen very well with an organic solvent if you sprayed it, right?
Because of the stability.
It won't work. There is another way to look at this, which could be very interesting, which is using inside-out microdroplets. What I'm referring to is micro bubbles or nano bubbles, even getting better. Okay, and this is another approach to this problem. Again, inexpensive and easy to set up. You need some porous medium that you let gas go through. You make now nano bubbles, etc. There's really so much here, and a number of us, I join you in thinking that a lot of chemistry can be done this way, and it's green chemistry. It's environmentally friendly, sustainable.
Because most of the time, even if you use water byproduct, again, if you look the reaction mechanism, it will be a water again. That's the advantage.